Hello, welcome to another brief video lesson on variable stars, group extrinsic. The group extrinsic variable stars cover variable classes eclipsing, rotating, and microlensing. This group of stars is classified based on external factors that cause changes to the star and thus variability to the flux that we receive. If you're familiar with this diagram, we've seen this before. This particular will be group extrinsic that we will discuss today. Let's focus on eclipsing binaries. Eclipsing binaries are binary star systems whose members eclipse one another, blocking one's light from the other, causing the system to look fainter to observers on Earth. The light curve of an eclipsing binary depends on the sizes and the brightness of the stars, how far apart they are from each other, or the geometry of our view of the system from Earth. If one star is large, it may totally eclipse the second, while the second only partially eclipses the first. The time between these eclipses is the orbital period of the binary system. So if you look to this image on the right, we have a particular system here. Note how the two stars are not fully aligned, so we won't get a true eclipsing effect, but you will get some blocking of the light. And so what you have is a primary dip here in the light, with a secondary is this B6 star comes back around. The time between this primary dip and this primary dip is the orbital time of this particular system. Detailed analysis of the light curve shape yields a lot of information about size, mass, shape of the stars, and the shape of their orbits, which we're going to talk about here in just a second. First, I want to discuss something called Roche lobes. We have previously talked about Roche lobes in other videos when we have talked about the difference between novae and supernovae. Modern classification schemes of binaries, including eclipsing binaries, are based on the concepts of Roche lobes and Lagrange points. So what are they? Let me draw a simple diagram here. If I've got one star and I've got another star, what we have are these areas. We'll call this area 1 and we'll call this area 2. Well, the first star, its gravitational field fills area 1. The secondary star, its gravitational control, fills area 2. What we have here in the middle is something called a Lagrange point. A Lagrange point is a place where the gravitational effects of one body are exactly equal to the gravitational effects of another body. So it's a point of neutrality, if you will. You could place a satellite right in between these two points here, and it would neither be pulled in one direction nor the other. It would be at a gravitationally neutral point. So that's what a Lagrange point is relative to Roche lobes, which is the area of gravitational control of a particular star system. Here on the right, we're going to talk about these Roche lobes. Semi-detached or detached binaries first are systems where both components are well within their Roche lobes, and the stars are still nearly spherical, like our sun, and total distortion of the star is minimal. So this is the case here of a detached binary system. You can see the Roche lobes defined outside of the two stars with a Lagrange point located right in between the two. So this is the case of a detached binary that are orbiting around each other. Semi-detached binaries are systems where one star fills its Roche lobe and becomes distorted. It's not spherical anymore, become ellipsoidal. It's probably losing its mass through accretion and through the inner Lagrange point onto the comparison star. So if we look at semi-detached binaries here, we can see that this particular star has filled its Lagrange point, filled its Roche lobe to the Lagrange point, and in most cases is probably accreting through to the secondary star. So the gravitational effects are starting to use that Lagrange as a funnel and accreting some matter onto the secondary star. So that's a semi-detached binary. Contact binaries occur when both stars fill their Roche lobes and are essentially in contact with each other. In some cases, they have a common envelope of material that blurs the distinction between individual stars and may surround the pair. These are often referred to as common envelope or over-contact binaries, and we see those located down here. Note that the stars in each of these cases are becoming ellipsoidal and no longer spherical, as we saw in the detached binary case. Agol variables. Eagle is a very popular eclipsing binary that's gone back many thousands of years and is highlighted every year or every month in Sky and Telescope magazine, where it gives you the eclipsing times of this particular system. So these eclipsing systems, these types of variables, contain spherical or slightly ellipsoidal components. The precise moments at the beginning of ending of the eclipses are well defined by their light curves, as you can see here on the right side. You can see when this primary eclipse begins, what its minima is, and when it ends. You can also note that for the secondary. Remember, from the primary to the primary, this is the period in time of these particular eclipsing binary pairs. This light curve is essentially flat between eclipses, but may vary slightly due to the ellipsoidal or physical variability of the components or their rotation or their reflection effects. What's a reflection effect? If two stars orbit each other very closely, some of the energy from each star will strike its companion. That'll be absorbed and re-emitted back out as a luminosity effect, as extra flux that we receive. The side of the star facing its companion becomes hotter and thus brighter than the side that's facing away. So this reflection effect from one to the other can have an impact on light curves. Here's another classic example, W-UMA. It's an eclipsing variable containing ellipsoidal components nearly in contact as they orbit a common center of mass. So our Roche lobes in this case are filled. The exact times of the onset and the end of an eclipse are possible to determine because these things are practically touching. And so whereas in the previous one we could see a very distinct pattern in the eclipses, that's not the case for UMAs. You can see a relative primary dip here and a secondary, but there really isn't a flat light curve position between the two eclipses. So we see this kind of fluctuation all the time in their light curves. Their characteristics are the stars have expanded beyond the Roche limits. Over contact or contact binaries are the case. These typically happen in the spectral class F or cooler stars. The light curve periods are less than a day. The minima are of near equal depth, so the primary to the secondary are very close to each other in brightness. These depths can change over time and cycle to cycle, so they're not always constant. Beta Lyrae type videos, another common type of variable star. Eclipsing variables contain ellipsoidal components here. The exact times and the onsets are impossible to determine because of the brightness of the system. These look like the W-UMAs that we just saw in the previous. Very similar. There's always a secondary minima. The depth of the secondary eclipse is usually much shallower than the primary eclipse. Remember in the previous, the secondary was very close to the primary. Here they're shallower, but they're still in a constant change of variation. The current picture of Beta Lyrae is that it's an eclipsing binary in the stage of mass transfer between the components. So they're filling the Roche lobes and mass is being transferred through that Lagrange point. Another one, rotating variables. These are rapidly rotating stars, often in binary systems that undergo small amplitude changes, which may be due to spots on the star surface or sunspots like we have in our own. Stars with sizable sunspots may show significant variation in brightness as they rotate, as the brighter area of the surface are brought into view and thus removed. These bright spots also occur at the magnetic poles of magnetic type stars. Stars with ellipsoidal shapes can show these changes in brightness in the varying surfaces. In summary, this lesson we reviewed the class of extrinsic stars, of things outside the star or on the surface that are causing some changes. They're not intrinsic to the intrinsic internal atmosphere or astrophysical processes taking place. Thank you for your attention, and we look forward to seeing you on future brief video lessons.